Hello everyone, and welcome back to the series on multivariable calculus. Today we're going to be discussing a very important but slightly different topic compared to normal, and that is vector functions and the calculus on them. Up to this point, we've just been generalizing how to do derivatives and integrals in higher dimensions for scalar functions. That is, if I give you a number or a set of real numbers, you give me one number as the output. But now we're going to be discussing the calculus of what we call vector functions. That is, if I give you a particular number or numbers, you give me a particular vector in some vector space. Okay, so what exactly does that look like, and what do we even gain by creating these new things called vector functions? So let's quickly define these things. So we're going to define U is going to be a mapping from R to R2, potentially Rm. And let's assume that f and g are both functions from R into R. Then we're going to call ut equals ft vt a vector function. So this is what we're going to call a vector function, or single variable vector function, and obviously you can extend this to multivariable vector functions if you want to. Right? So I give you one real number as the input, and I give you a two-dimensional vector as the output. So let's start off, just like we did in pre-calculus. How do you graph vector functions? So let's assume that t is a real number, and somebody asks you, graph u of t equals minus t squared. So usually, like back in the day, what we usually do is we take a bunch of numbers, and then we create a table of values from it. So for example, we have t, and then we have u of t. So for example, we can do minus 2, minus 1, 0, 1, and 2, and see what those particular outputs are going to be equal to. So when we plug in minus 2, we're going to have minus 2, which is 2. So we're going to have the vector 2, 4. Plug in minus 1, that's going to give us 1, 1. Plug in 0, 0, 0. And then plug in 1, you get minus 1, 1, and then minus 4, minus 2, 4. So that gives us the output vectors for those input values of t. So what would that look like? So when t is equal to minus 2, we have the vector 2, 4, which is going to be that vector there. And then when I plug in t is equal to 1, so this is the t equals minus 2 vector. And then when I plug in t is equal to minus 1, I get the 1, 1 vector. And then when I plug in 0, I get the 0, 0 vector. When I plug in 1, I'm going to get the minus 1, 1 vector. And then when I plug in 2, I get the minus 2, 4 vector, which I guess would be right there. So how do we graph vector functions? So obviously when t is negative, we have values here, and the endpoints are going to slowly hit all of those tail points, and then they're going to hit all of the tail points on the left-hand side. And then you get, I guess, the graph of a parabola. So what you actually have here, once we sketch it, is indeed the graph of a parabola. The only difference is we now have direction, because vectors have magnitude and direction. So pretty much this is the graph of our u of t, where this is the x and y components. Right? So the vector functions have graphs that compose both position and also speed and direction. So let's actually mention that, because that's actually quite important. So this graph allows for both speed, like velocity, so that would be tempted to say the derivative of this vector function, whatever that means, and also direction. Rather than just location, like we did for a parabola, which would just be that. So after t is equal to 5, where would you be? That parabola would give you those answers, right? So we have speed, direction, and also position at least relative position, when it comes to vector functions. So now that we know kind of what a vector function is and what it represents and how to graph them, let's define some calculus principles on them. All right, so let's start off with the basics. So we're going to define the limit as t approaches a of u of t. Keep in mind u of t is a vector function now. And this is going to be defined to be equal to, and let's assume this is a two-dimensional output. So this will be the limit as t goes to a of f of t, and the limit as t approaches a of g of d. So the limit of a vector function is defined to be equal to the limit of the individual components of that vector. So if we have limits from it, we can build derivatives. So the derivative with respect to t of a vector function u of t, this will be defined to be equal to the limit as h approaches 0 of u of t plus h minus u of t all over h. Now, it might look like we're dealing with the same exact definition from single variable calculus, but this is not the same, because what is u? U is a vector. That means u of t plus h is a vector. U of t is a vector. Therefore, vector minus vector is vector divided by a scalar. That's still a vector. So that means the derivative of a vector with respect to a variable t will also be a vector as well. So what exactly does this mean, and what do we get from its definition? So true or false is the derivative of a vector equal to the derivative of the components of that vector. From the limit definition, you should be able to verify that that is indeed the case. So how would you prove that? So that means this is going to be equal to the limit as h approaches 0. H approaches 0 of, so u of t plus h. So you do that for f, you do that for g. So this is going to be equal to f of t plus h minus f of t all over h, and then g of t plus h minus g of t all over h. And obviously there's a couple small steps skipped between these two statements, but you should be able to verify. So this is still just a vector. So the limit of a vector is just equal to the vector of its limits. So that will distribute into it. So you're going to have the limit as h approaches 0 of f of t plus h minus f of t over h, and the limit as h approaches 0 of g of t plus h minus g of t all over h. And this precisely is the definition of the derivatives of f and g, assuming that they're actually differentiable functions. All right, so we have f prime of t and g prime of t. So that means the derivative of a vector will just be equal to the derivative of the components for that vector. And we could also say as a corollary that a vector function is differentiable if and only if its components are differentiable functions as well. Obviously, once we start defining derivatives, we're obviously going to get a boatload of properties associated to them, and here are some of the basic ones, and you can prove these on your own. They're actually not too tricky. So for example, if we have two vector functions u and v, then the derivative of the sum of those vectors, because keep in mind, vector plus vector is also a vector, so the derivative will also be a vector, will be equal to the sum of the derivatives of the individual vectors, provided that those vectors are indeed differentiable. Right? So derivatives are linear operators, at least it appears to be, especially if the second property is true. So if we have f a scalar function, u a vector function, and we scale that vector by that scalar function, then what you actually have here is a product rule of sorts, fu prime plus f prime u. Almost looks like a product rule, and the proof pretty much follows the same exact structure. The only thing I really need to mention, and for you to be careful of, is that this is a scalar function, this is a vector function, this is a scalar function, this is a vector function. A scalar times a vector function is a vector function. A scalar times a vector function, again, is a scalar vector function. And a vector plus a vector will also be a vector, because y, the derivative of a scaled vector, is still the derivative of a vector, which is a vector. So make sure every time you're working with these new structures that they assume and take the right type that they should. For example, If we take the derivative of the composition of u with f, so you take f as the input of vector u, because why? Well, f of t returns a value r, and therefore we can use that output of f as the input of u, and we can define the derivative of u composed with f of t, and that will take a chain rule of sorts, so u prime evaluated at the original output times the derivative of the scalar function f prime. So again, we have our scalar function here, we have our vector function here, and scalar times a vector will be a vector as usual. So I want you to take a moment and maybe think about, does the statement, the derivative of f of u of t, make sense? And if so, would it be equal to f prime of u of t times u prime of t? So make sure to take a moment and think about that, because understanding whether this does make sense or not is extremely important. But nonetheless, these three properties, which are indeed true, don't really offer anything new, because they're pretty much generalizations or new forms of the original single variable product rule and chain rule. So what I want to do now is introduce a theorem that is actually quite unique to the realm of vector functions, and that is the following. So suppose that u and v both send r to R2, and then let's consider the derivative of the dot product between them. What will this be equal to? So let's see if we can actually prove this statement without actually knowing what we're actually proving. So because we know the dot product of two vectors will be a scalar function, right? So vector dot product with a vector is a scalar, so we should get a scalar function as our answer. So what will that scalar function be? Well, we're about to find out. So this is going to be equal to what? So that's going to be equal to the derivative of, so again, let's call it, how do I want to call this function? Let's call it f and g for both u and v, just fu gu, fv gv. So this is going to be equal to, let's call it fu of t, and then gu of t, dot product with fv of t and gv of t. And we know how to find the dot product of the vectors. It's just the sum of the inner products with the components of those vectors. So this is going to be equal to the derivative of fut fvt plus gut and gvt. Now here we have scalar function, that's a scalar function, and the derivative of the scalar function goes back to the single variable product rule, and we also have a product rule for the GU-GV product as well. So what is that going to be? So it's going to be first times the derivative of the second plus the second times the derivative of the first. So that's the first product rule. And again, first times the derivative of the second plus the second times the derivative of the first. So that's the derivative of the second. So now what I want to do is I want to regroup everything. I want to bring this term over here, and I want to bring this term over here. And that's going to give us f of u t, f of v prime t, plus gut times gv prime t as a term. And then I'm going to have fvt, fu prime t, and then gvt with, I'm missing a derivative, first row second plus second derivative of first, so gu prime t. All right. So what have I done here? I've grouped the derivatives of v here, right? So that's the derivative of v. And over here I have the derivative of u. Right, so that's u prime, and this is the v prime set. So notice that this is just equal to f and g, that's just u, and notice I have v and v, that's just v. So I can write this as the dot product of fut, gut, dot product with f prime v, and then g prime v. And then plus, I can write this as f prime ut, g prime ut dot product with fvt gvt. So what is this? Well, this by definition is going to be what? So that means the derivative of ut dot product with vt will be equal to ut dot product with v prime t plus u prime t dot product with vt. Right? Also keep in mind dot products are commutative, so you can exchange those orders if you want to. So what do we have? It looks almost like a product rule, but keep in mind this product rule is slightly different because this is a derivative of the dot product between two vector functions. All right? So one could ask, consider the following theorem. Let's assume that u and v both send r to r3. Then what can you tell me about the derivative of the cross product between u and v? So what you actually get here is ut cross product with v prime t, and then u prime t cross product with v of t. So you'll get this. Right? So that's actually quite interesting. Now, a couple structural things. Keep in mind the dot product between two functions is a scalar. So here we have a scalar function plus a scalar function. This will be a scalar function as the output. But if you take two vectors in R3 and you take the cross product of them, that will be a vector. So here we have a vector plus a vector. This will be a vector function. Right? So we here clearly have those important properties that are unique for vector functions. And one can say, well, if you can take derivatives of vector functions, can you take the integral of them? The answer, of course, will be yes, as long as they are integrable. So the integral from a to b of vector function u of t dt will be equal to, and defined to be equal to, the integral of the individual scalar function components. So the integral from a to b of f of t dt, and the integral from a to b of g to t dt. So as long as the components are Riemann integrable, then the vector function is said to be Riemann integrable with this particular structure. And then you have several other things, such as integration by parts and u substitution and change of variables associated with that, but I'll let you explore that since you now have the definition of it. It may be pretty obvious, but that since vector functions are just vectors, they will also have magnitudes. So let's take for a very basic example, u of t is equal to r cosine t, r sine t, where t ranges from minus infinity to infinity. So do you want to take a guess of what this vector function looks like? So if this is x and this is y, let's say, then you should know that this is the vector function representing a circle of radius r. So this is the point r0, this is the point 0r, this is minus r0, and this is 0 minus r, where the orientation is counterclockwise. And you should be able to verify that. All right, so since it's a vector, it also has the magnitude. So what is the magnitude of this particular vector? So the norm of u of t will be equal to the square root of the sum of the squares of its components. So r squared cosine squared t plus r squared sine squared t. I can factor out an r squared out of both terms and then take the square root, assume r is positive, and then that's just going to give me r. And then we have the cosine squared t plus sine squared t. Cosine squared plus sine squared is just equal to 1 by the Pythagorean identity. So we have r times the square root of 1, which we know to be equal to r. Right? And note this is true for all t in r. Right? So it's independent of t. So that means it has the same exact size for all time. So what does that mean? So that means in some sense the distance from the origin to the boundary stays the same. And that's sometimes why people define this as a circle. Right? It's a set of points that are equidistant from its center. So let's find the derivative of this vector function. So that's going to be equal to what? So it's going to be equal to minus r sine of t, r cosine of t. So what would its norm be equal to? So the norm of u prime t will be equal to, again, the square root of minus r squared sine squared t plus r squared cosine squared t, and you should be able to see that that's also equal to r. Since we have a derivative vector, or some people also call it a tangent or velocity vector, some people actually only care about the direction, not necessarily the size. So this is what motivates the existence of the definition of a unit tangent vector, t of t, which is just the tangent vector u prime of t divided by its norm. Right, so this is a unit tangent vector. Unit tangent vector. So that means for our particular example, what we have here is that the unit tangent vector will be equal to the derivative vector, which is just going to be equal to what? So that's going to be minus r sine of t, and then r cosine of t, divided by its magnitude, which is r, which will be equal to minus sine of t, and then cosine of t. It's very important to note that the norm of the unit tangent vector will always be equal to 1 for all t. Right? Then another question that somebody might be able to ask is that, yes, the vector function is changing direction, but how fast is it changing direction? So how fast is the curve turning at any time t? This obviously is reminiscent from single variable calculus from the perspective of acceleration, and acceleration is the derivative of velocity, but from the perspective of curves and geometries, this is what we refer to as curvature. Curvature. So the definition of curvature is going to be as follows. So the curvature, kappa, of t is defined to be equal to the norm of the derivative of the unit tangent vector at time t, right? So keep in mind what that is. So the tangent vector is the derivative, so t prime is the derivative of the original function, its norm, divided by the norm of u prime t, right? So how fast is the curve changing with respect to the original curve, which was u prime of t. So we divide it by its norm to get a normalized value. Right? So keep in mind, this is going to be a number, not a vector. Right? Because it's norm divided by norm, that's just a number. So if we look at our particular example, what is that going to be? So again, let's assume that u of t is equal to r cosine of t, r sine of t, where t is real. So u prime of t came out to minus r sine of t, r cosine of t. And from it, we found that the norm of the velocity vector was equal to r. From the velocity vector, we are able to get the unit tangent vector, which again is u prime of t divided by its norm, which we found to be equal to the vector minus sine t cosine t. And that minus sign is associated to sine, not cosine. So once you have the unit tangent vector, then we can differentiate it. So the derivative of the tangent vector, which you could call the acceleration vector, will be equal to what? So that's going to be minus cosine of t and then minus sine t. Minus sine t. And then the norm of the acceleration vector will be equal to, and you should be able to verify that that's going to be equal to 1. So therefore, what is the curvature of a circle of radius r at time t? So we have all of the components, so therefore the curvature at any time t, again, is the absolute value of the acceleration vector divided by the absolute value of the velocity vector. The absolute value of t prime t came out to be equal to 1, and the absolute value of u prime t came out to be equal to r. So we have 1 over r. So what does this mean? So that means the smaller smaller the circle, smaller the value of r, the larger the curvature, and the larger the circle, larger the area, larger the radius, the smaller the curvature. And think about it from a geometric perspective. For example, you have this circle here, and you have this larger circle here. Right? So the larger circle, you don't need to turn as fast, but with the smaller circle, you have to turn quite fast. Right? So smaller the circle, larger the curvature, larger the circle, smaller the curvature, and we've proven it for a circle. Right? So that's pretty nice. Another very important thing that you definitely should know in regards to vector functions is arc length. Arc length. Now, we discussed arc length back in the single variable calculus world. So what did we say? So if we have, for example, some function here, and let's assume that this here is u of a, right? And let's assume that here, this is u of b. And let's assume, obviously, that we're traversing in this particular direction. And in this particular picture, this vector here, that would be u prime of a. And this vector here, that would be u prime of b. So a question that you could ask is, what is the area or the length of that arc that is traversed by this particular vector function? Right? So arc length equals question mark. In the single variable calculus world, we're like, oh, can we just approximate the lengths of the hypotenuses of the triangles that sort of approximate that particular length? And the answer obviously was yes. So we're like, okay, find that hypotenuse, that hypotenuse, that hypotenuse, and add infinitesimally. So for example, if r prime of t, or let's call it u prime of t to stay consistent, so u prime of t was equal to f prime of t g prime of t, then the norm of u prime of t would be equal to what? Well, it's obviously going to be equal to f prime of t squared plus g prime of t squared, if that is the case. And from our geometrical perspective, the arc length L will be equal to the integral from a to b. And parametrically, we've defined this already and proven this already. But that's going to be dx dt the quantity squared plus dy dt the quantity squared dt. Because keep in mind we have dt squared, so this is actually equivalent to the integral from a to b of dx squared plus dy squared, right, without the dt on the outside. So you can be like, oh, well, what is this? Well, this is just the norm of the derivative of the vector function. And indeed, that would be the case. So that means L would be equal to the integral from a to b of the norm of u prime of t dt. Right? So we have this very simplistic representation for finding the arc length, or the length of the path traversed by the vector function from t is equal to a to t is equal to b. So this path doesn't even need to be nice. For example, your path could technically be this. So for example, these could be your endpoints. So this could be u of a, and this point could be u of b. And if I want to find the length of that string, that would just be equal to L. So it's actually quite easy to do it with vector functions. As a very basic trivial example, of course, I'm going to use a circle. So remember, u prime of t, circle of radius r, was equal to r, and that was true for all t. And let's assume that t belongs to the interval 0 to 2 pi, so you only traverse the circle once. So then the arc length, or the circumference of the circle, will be equal to 0 to 2 pi in terms of t, and then the norm of the function u prime t at all time t, which is r, dt. Notice that our integrand does not have anything with t in it, so that's just a constant. So this is just going to be equal to 2 pi r, which you should recognize as the circumference of a circle. Isn't that nice? So this was just a vector function fundamentals video that sort of introduced you to the very important mechanisms associated with vector functions, in particular the derivatives of scalar functions times vector functions, dot products between vector functions, cross products when defined between vector functions, and also how you define integrals, curvature, and the arc length for vector functions as well, which has an immense number of applications in the outside world. Hope you enjoyed this video, and I'll see you in the next one. Take care.